So I start this session on the decision theoretic aspects of ambiguity. So I guess I've been selected endogenously to be the first presenter, which means I will have also to do a little bit of survey. And in fact, as you will see, a large part of what I'm going to be talking about is going to be on the survey side, because I mean, I can go on talking for about 2 hours, but that's not what you want from me. Okay, so in general, let me make another premise, which is, as I was discussing now with Bob Anderson, it's not totally clear exactly what I am doing here. I mean, I'm useful as a tool of, the tool of showing to you a certain number of models. But it seems also fairly clear to me, and I'm open to be convinced otherwise, that from the viewpoint of the people working in the area, either the economists or the scientists, there seems to be no ambiguity on policy, which is, okay, you know what, let's just do max-mean here. Okay, you can call it the precautionary principle, we call it max-mean, but it's the same thing. The idea is, let's try to gauge the ambiguity, like what we know about the phenomenon, and then let's take the max-mean prescription. Unfortunately, as it happens, I have been working on non-max-mean models, and so to some extent, what I can tell you, which is mine, is less relevant to this group. I will also, what I've been working on, and I'm going to be telling about you here, is also a little bit of, obviously, the kind of divertissements that theorists work on, which is exactly what do we mean by ambiguity, what do we mean by ambiguity aversion, is there a way that we can actually observe it from preferences, okay? So the kind of things that, honestly, in applied endeavors, who gives a hoot about these things? In applied endeavors, you just assume, you assume what the set of priors is, and you just do policy on that. Of course, assuming in some sense, in some cases, requires years and years and years of scientific work, most of which, is as yet incomplete. But from the viewpoint of doing the decision theory, the decision analysis, there is nothing terribly deep. Anyway, what I will try to do here is do the explain, show to you some of the models, and then tell you what do we think right now, or what I think and some other people, my co-authors in particular, think are ways of describing ambiguity formally and describing ambiguity aversion formally. So in case you are interested in the foundations, conceptual foundations of these concepts, here is where we stand right now. So this is work that I've done. This is what I'm going to be talking about is mostly work that I've done with a number of co-authors, Fabio Maccheroni, Massimo Marinacci, and Marciano Siniscalchi. So from the very beginning of economists and statisticians thinking about these things, multiple priors has been considered to be the natural way of modeling a perception of ambiguity. And here I put a reference to Savage. There is no mistake. This is the reference to the Dover edition of the Foundation of Statistics. If you read the Dover edition of the Foundation of Statistics, you will notice that there is a passage in which Savage added a footnote in the second edition, where the passage is a fairly often quoted one, the one in which he says, one of the main problems of my theory is that sometimes probabilities are vague, and I don't know how to model this. So this was what he wrote in 1954. In 1972, he added a footnote, and he said, I think now I have an idea of how this could be done, multiple priors. Okay, so that's why it's Savage 72. So the idea of using, of course, multiple priors had been used before by statisticians like Dempster, Smith, and so on, and so they were already, that's why Savage was already aware of these things. So it's been ever since, the 70s or late 60s, it's been thought that this is a natural way to look at ambiguity. Now, many of the modern models of choice in the presence of ambiguity employ multiple probabilities to capture ambiguity, and here are some examples. well-known one, the max-mean expected utility model of Guilbault and Schmeidler. Of course, most of these ideas were precede this, what I give you as a reference. What I give you as a reference is the axiomatization. Okay, so when is it that we actually found a representation theorem that says if preferences satisfy these properties, then we get this type of representation. So max-mean expected utility, I'm going to be telling you what these models are in a minute. So let me just go through them quickly. Another model which is more recent and is becoming more and more popular in applications is what Sujoy is going to be talking about, the smooth ambiguity model, which nowadays we call the KMM model, Klibanov, Marinacci, Mukherji. There are also other people that have developed variants of the model, Ergin and Gould and Seo have been, and of course, I forgot also Bob Now, worked on similar ideas. Even more recently, there is the variational preferences model of Maccheroni, Marinacci, and Rustichini, and then a slew of papers which kind of take the same ideas and modify them, culminating with the general uncertainty averse preference model, which is due actually to at least two of those people, and Simone Cerea-Vioglio. So these are all models that more or less explicitly use the idea of multiple priors. Now, in max-mean, it's clear. Max-mean, you say there is a set of priors. I calculate the expected utility of every possible option that I'm evaluating according to which one of the priors. I take the worst-case scenario evaluation as my evaluation of my policies, and I decide which one is the policy that maximizes this mean expected utility. Smooth ambiguity involves the sets of priors in a way which is a little more subtle, we will see, but it's still fairly obvious. And also, all these models involve multiple priors one way or the other. There are other models which are also popular that do so in a less obvious fashion. The obvious example is the Choquet expected utility model of Schmeidler. Choquet expected utility model actually does not use multiple priors. It uses a different object, which is a non-additive probability called the capacity. Turns out, however, it's a ruse. The Choquet expected utility model is yet another model of multiple priors, okay, in disguise, and I'll show you exactly what I mean. My co-author, Marciano Siniscalchi, has also written a model which is called vector expected utility, which is also somewhat related to one of the models that I discussed in the previous slide. And again, vector expected utility apparently doesn't seem to be using multiple priors, but it's not true. As I want to argue in the research I'm talking about, these models all involve multiple priors. It's just that it's not obvious how. Okay, so what I will do is I'll briefly report on two papers of mine. One is Christian has already identified correctly as being relevant to my talk. The other one, Christian is excused for not knowing that I'm working with Marciano on an update of that paper. And I apologize to all the economists in the audience. When I write GMM, I don't mean the generalized method of moments. I mean Ghirardato, Maccheroni, Marinacci. Unfortunately, in decision theory, this is, it's like KMM is Klibanov, Marinacci, Mukherji. GMM is Ghirardato, Maccheroni, Marinacci. Okay, the long-term objective of this kind of research that I'm telling you about is provide behavioral foundation for the idea of multiple priors, and ideally, and here, of course, you can argue with me whether we are successful or not, provide a compelling separation between ambiguity and ambiguity attitude. Okay, one of the problems in the literature from the very beginning has been that if you think about the max-mean expected utility model, there seems to be a little bit of a confusion between ambiguity and the fact of being ambiguity averse to such ambiguity. Okay, in fact. To the point up to a few years ago, it was basically kind of held that ambiguity aversion determines the size of a set of priors. So that in a sense, the set of priors and the fact that you're ambiguity averse are linked together. What we're going to argue here is that that's not true. Okay, that there is a way of identifying the priors on one side and identifying the ambiguity aversion in the other side. You may disagree with me as to as to whether this is the right way of doing this, but at least we suggest a way of doing it, okay? Okay, so here, let me be useful for a few minutes, and then I'll start being useless. So first, a brief review of some of the basic models. First of all, max-min expected utility. In max-min expected utility, the decision maker's preferences are represented by a functional V. Define F is going to be my letter for your policies, options, portfolios, however you want to call your possible choices. So your preferences are represented by this, oh, there is a pointer, right? By this functional here. You have a set D, which is a convex, closed, and well, unique set of priors. So a set of possible scenarios, probabilistic scenarios. Your decision maker, what does your decision maker do? It calculates for every possible action the expected utility. U is a standard Bernoulli utility index. Calculates expected utility and then takes worst case scenario approach. This is familiar, and I've already described it in words to you. Choquet expected utility is apparently different. No, not really when you just look at it this way, but there is a major difference, which is rather than having a set of probabilities, in Choquet expected utility you have V, which is a capacity. A capacity is a set function that is not necessarily finitely additive, okay? So this is even worse than what Definetti was arguing with other people about. It's not that we don't want to have countable additivity. We don't want to have additivity altogether, okay? It's worse. So this was proposed by David Schmeidler. Both of these, of course, and I hope, I'm going to skip this part, both of these models explain behavior like the one in the Ellsberg paradox. I'm going to be giving you a version of the Ellsberg paradox in a few minutes anyway. So this is like the standard stuff. Remark, the max-min expected utility model necessarily entails an aversion to ambiguity by construction. I mean, the word min clearly tells you aversion. Whereas the Choquet expected utility model does not necessarily, okay? Choquet expected utility gives you aversion to ambiguity only under conditions on the capacity V. Certain capacities are averse to ambiguity, certain others are not, okay? You could actually be ambiguity loving with Choquet expected utility. And so there is no, so in a sense, Choquet is a little bit more flexible than max-min, which is one of the reasons why in the beginning of literature on applications, it was used more than max-min. And also because it was easier to deal with one integral rather than set. But okay, more recently, variational preferences is a model introduced by Maccheroni, Marinacci, and Rustichini. It's somewhat similar to, it's a direct generalization of max-min. Here what you do is, BA1 is just a set of all finitely additive probabilities over the state space. So what you do is you calculate for each measure the expected utility it gives you, and then you have this C function, which they call a cost function. It is basically as if nature is out to get you, but she has a cost function, okay? She cannot use every prior with the same cost. Some priors are more costly for her, and so that has to be taken into account, okay? And so, for instance, one example of a typical cost function is relative entropy with respect to another measure, okay? So with respect to some baseline, and we'll see an example of this type of models later. And oh yes, I'm sorry, I've been already using this notation. No, let me introduce this notation. Q of A is going to be my shorthand for integral of A with respect to Q, okay? Another variant of this is confidence function preferences. Let me just go quickly on this. This is a very recent model. More recently, the same guys have shown that basically all of these models can be captured into a general model, which they call uncertainty-averse preferences, which has this unifying representation. Instead of, basically the idea is, why do we have to add here? Why don't we just imagine having a function g which is non-decreasing and has some nice properties, quasi-convexity, reflecting again ambiguity aversion, as a way of generalizing this idea, and this is the uncertainty-averse preferences. Okay, so we're getting worse. We're going into the heliosphere here in terms of generality. All of these models I want to point out, all of the three of these are models which build on an ambiguity aversion assumption, okay, which axiomatically is explicitly seen. It's called the ambiguity hedging axiom. I can show it to you later. Another model, smooth ambiguity. Our speaker, the next speaker, is going to tell you much more about this. The idea here is, it's a natural idea again. Suppose that instead of having, so first of all, there is a possible set of priors, and over the set of priors, you have a probability, a second order probability, mu. However, instead of doing, definitive would have said, okay, when you have a second order probability, well, what you do is you just, you calculate, do the reduction of compound lotteries, calculate the prior, the single prior over the state space, and you do expected utility over that. This is not what you do here. What you do is instead, you calculate the expected utility corresponding to each scenario, and then you distort it, if you want, using this phi function, which you can call second order utility. If this phi function is, say, concave, then this gives rise to a decision rule which is ambiguity averse, which gives rise to the same, the same preferences as you see in the Ellsberg paradox. And again, Sujoy is going to tell you more about this, so I'm going to be moving quickly over this. Okay? A special case of this is well known in economics these days, in macroeconomics especially, because it's been pioneered by Hansen and Sargent and their co-authors. Is the so-called multiplier preferences model, which looks like this. Now, as it is written here, it doesn't look like a special case of the smooth ambiguity model, but it is. Okay, this has been, it's actually kind of a triviality, but it's also, for instance, shown explicitly in a paper by Tomasz Strzelecki. Again, it looks like variation. This is kind of a variational preference type of preference, where the cost function is given by theta, which is your personal ambiguity aversion coefficient, times relative entropy of Q with respect to some baseline measure P. So here you have some idea, P, which is your baseline assessment of what could be the truth, and then you give a cost of the function which is bigger as you get away in terms of entropy from P. Finally, this is my co-author's Marciano Siniscalchi's model. We have also the vector expected utility model. Here, what you do is you have a baseline probability again. So there is a kind of a focal idea of what the probability is. But then you have some adjustment factors. So your evaluation of any, here should be an F again, but I'm sorry. Your evaluation of any possible option is given by your baseline evaluation, and then you have some adjustment coefficient. And now if this function A has certain properties, then this can build the ambiguity aversion or ambiguity loving and so on. Okay, what have I done here? Okay, so these are this very quick overview. I'm sorry I cannot be much deeper into this. So let me go back to the objective of what of my research rather than my talk. So the question is, can we obtain a set of priors which represents subjective ambiguity? Okay, so again, here I'm not dabbling with the deep issues of what should be the ambiguity in reality and things like this. Here is like, I have a decision maker. This decision maker has preferences. I want to try to identify this from this decision maker's preferences, what appears to be her perception of ambiguity of a problem. Okay? For instance, I might want to do this because there is some objective ambiguity out there, and I want to make sure that the subjective ambiguity is consistent with the objective ambiguity. I want to say, well, let's imagine I have a decision maker who knows about the objective evidence and is consistent and has preferences which are consistent with this. Okay? How can I do this check? Well, in order to do this check, I need to have a theory of subjective ambiguity, which is what we want to develop here. The other question is, so can we obtain a set of priors? In particular, do we need restrictive assumptions, such as ambiguity aversion or hedging, which is a slightly stronger condition, or certainty independence, which is one of the axioms that is crucial in building, say, the max-min model or the Choquet model. Okay, so is there a way to generate a theory of multiple priors that doesn't require, for instance, doesn't require the assumption ex ante that the decision maker is ambiguity averse? And so here, very briefly, why do we care about relaxing both ambiguity aversion and certain independence? Well, as I said, in this group of people, you may not care about relaxing ambiguity aversion, but in general, when we are discussing about modeling people, then there is abundant evidence that uniform ambiguity aversion in any one of its forms is too restrictive. These are some papers. Just one example, a couple of examples of psychological papers. Heath and Tversky show that, for instance, when people, when you have to make bets which are on things which are based on your competence, then you tend to be ambiguity loving rather than ambiguity averse. That's it's a famous example. Hogarth and Einon is another example. There is also a more recent literature in economics, a very nice paper due to Mark Machina, and then a comment and generalization due to Bayonne et al., which shows also that there are some very intuitive examples where the type of behavior you would expect people to display in this example violates extreme ambiguity aversion. Okay, so if you want to make the kind of choices that you think people would make in that situation, then you cannot have extreme ambiguity aversion. So you cannot have max-min as your preference choice. As to CI, certainty independence, why do we want to violate certainty independence? Certainty independence, in a sense, is an axiom that says that your reaction to ambiguity is wealth independent. Okay, I mean, if I boil it down to the essentials, that's it. Now, of course, economists by now consider it to be totally trivial that people's risk aversion is wealth dependent. Now, the question is, why should ambiguity aversion be wealth independent? So that's why, theoretically, you would like to imagine a situation where a theory where you don't require make this additional assumption. And of course, many of the preference models that I just presented to you violate certainty independence. The more recent ones, the literature, starting from 2005 on, are all models that violate certainty independence. So that's one of the reasons why we want to have a theory of ambiguity that applies. We want to have a theory of ambiguity that applies to these models. That's why we need to violate. All right, this is quite a mouthful. It's, the technical details I don't think you're really concerned about. We work in a mostly standard environment. Just remember, S is going to be my definition of states. X is going to be my set of consequences. I'm going to assume that it's a convex set. So we are working in what decision theory call an Anscombe-Aumann environment. I want to think about the possibility of results which are lotteries over final prizes. All of this stuff we can skip and come back to it later. This is, again, some other. OK, shorthand notation I've already introduced. OK, let me give you the basic intuition for our way of obtaining subjective ambiguity. And of course, the basic intuition is Ellsberg again. So this is the famous Ellsberg paradox. You probably know about it. You have an urn containing 90 balls, 30 are red, 60 are either blue or green. Of course, here they were supposed to be colored, but you cannot tell the colors on the screen. For several individuals, if I ask you, would you rather have $1 if red or 0 if otherwise, they prefer this to $1 if blue. Now, instead of giving you the traditional version, let me give you this other variant, which is, suppose I give you the possibility of flipping a coin, and if a coin comes up heads, I'm going to pay you. I'm going to be giving you the lottery over blue, otherwise green. Would you rather have this, or would you rather have the one in which I get red here and green there? This has never been done, actually, but we conjecture that, notice that basically this is like betting on blue or green with a half of as price instead of 0. And we conjecture that the kind of preferences that people would display are the same as in the Ellsberg paradox. And so what you do see here is that the presence of ambiguity is revealed in preference-wise by the possibility of reversing the preferences of 1R over 1B just by mixing both of them with G. Okay? So this is the idea of our construction of a set of priors. So the above motivates the following definition. I'm going to say, given two possible actions, F and G, that F is unambiguously preferred to G, and I will denote it F squiggle star G, if basically every mixture of F with some other act is preferred to every mixture of G with some other act. Okay, so if this kind of reversals that I just showed you in the previous slides don't happen, if these reversals are not shown, then I am going to say that F is unambiguously preferred to G. Okay, it's a kind of very strict definition of preference. In this way, I construct, if the original preference that I started from satisfies some basic properties, I'm going to be flashing them in front of your eyes later, then the squiggle star derived relation satisfies some standard properties. It's reflexive, monotonic, continuous. It's independent. And it's a coarsening of the original preference that agrees on the original preference on the constants. So what you can do is you can now define a set of probabilities via a result which is really a folk theorem now. We usually attribute it to Truman-Bewley. The MBC preference represented by AU, don't read. You're going to understand it later. Basically, given a well-behaved squiggle preference, if you define squiggle star as above, then there exists a non-empty, unique, convex, and weak star closed set C of probabilities such that F is unambiguously preferred to G if and only if every prior in the set C prefers F to G. So if there is a unanimity, is a kind of a Pareto unanimous rule that says, is F better than G according to every scenario, then F is unambiguously better than G. Okay? So this is the basic idea for the construction of the ambiguity. What I'm going to suggest is take any preference that satisfies one of the models that I've shown you before, construct the squiggle star relation, and then the representation of this relation is going to have generate this set of priors, and this is what I'm going to call the ambiguity in the problem. Okay, for future reference, I'm going to be calling crisp any act whose evaluation is independent of a prior. So any act which is given exactly the same expected utility by all the priors in C. So let me just, so as I said, the model that we are using is very general because it has to encompass all these other models. These are the axioms. Let me just go too quickly for you to understand. But basically the idea is weak order is an obvious assumption. Monotonicity is another obvious assumption. Then we have some weak, very weak independence conditions that we need for technical reasons. And then we need a continuity condition, which is really too long to explain carefully, but it's a continuity assumption. And what we get, non-triviality, and we get this. So, you know, a decision maker that satisfies this very, I guarantee, they are very weak. Axioms has preferences which are represented by a utility function, which is the classical von Neumann-Morgenstern index, over the prices, and over the lotteries over the prices. And then there is a functional I that represents his preferences that has only these properties. It's monotonic, it's normalized, which is a big kind of natural condition, and it's continuous. Nothing else. It doesn't have any linearity properties. So in general, it's not an integral. Okay? The uniqueness part you really don't want to read. And so I'm going to be calling MBC, MBC stands for monotone, Bernoullian, and continuous. Any preference that satisfies the axioms that I didn't really show to you before. Given this, let's see, what should I take? 5 more minutes? Okay. Given this, I can, okay, so given this, I obtained the representation of ambiguity, okay? And I derived it in a way which you didn't really have time to digest it, but my point is, I think that's, a natural way of describing ambiguity. Now, given my derivation of ambiguity, now I can derive ambiguity aversion, because I can derive ambiguity aversion in a very trivial way, by the way, because then I can say, look, just tell me, the decision maker's preferences now are going to be sandwiched between the preferences of the max-min guy and the max-max guy, given C. And with a certain coefficient alpha, which is not going to be a constant, absolutely not, okay? except in the trivial cases. In fact, turns out, except in the trivial cases in which alpha is equal to uniformly 1, max min, or uniformly 0, max max. But in general, this is going to be my, so the preferences that I described, which are very, very weak, can always be represented in this alpha max min representation, but alpha non-constant. Now, this coefficient alpha can be shown, and here I have to go very quickly, can be shown to be a representation of the ambiguity aversion of a decision maker according to what is considered to be a fairly reasonable way of describing ambiguity aversion, more ambiguity aversion. And let me just skip this. So what I want to show to you now is the more practical part of the exercise, which is, okay, so you have given me a theory of how to, given preferences, how to identify the subjective ambiguity. Now, if I identify the subjective ambiguity, then I can identify subjective ambiguity attitude too, okay? But first, I need to identify subjective ambiguity. How do I do it? Do I really have to go and ask the decision maker 100,000 questions? Or is there a way to do this? Turns out that there is a mathematical way of doing this, and which allows me to construct the set C for a large class of models. Okay? The mathematical way of doing this goes via proving that the set C that we constructed is actually a derivative. So that in a sense, of course, I'm not saying that this is really practically much more helpful, but in a sense, if I know the decision maker's preferences, I can differentiate them and I can obtain the set of priors by differentiation. Now, let me just go through this very quickly. What we do, so this is all details about the construction of which derivative are we talking about. Of course, our functional is not linear, so we cannot go Gateau. Or gradients. That would be too easy. We have to use a general notion of derivative, which is due to Clark and Rockefeller. And this is the main result about this. The main result says that if you give me any preference that satisfies the previous axioms, then the set C that I constructed according to that decision theoretic criterion is the convexal of the union of all the possible derivatives, generalized derivatives, where I also have to take into account the fact that these are actually not necessarily probability measures, so I have to divide by QS. So it's the union of normalized differentials according to Clark-Rockefeller. Okay, so you might think that this is really mental masturbation. Turns out that it helps you calculating C for specific models. Okay, so let me skip to that quickly. So for instance, of course, in the MU case, unsurprisingly, we find that the set C is the set D, and which, by the way, goes to proving what I said before. The set of priors in the max-min case is the ambiguity, and the guy is really ambiguity averse. It's not that there was, that the set of priors was capturing ambiguity aversion in the same way. No, the guy is really extremely ambiguity averse. In the Choquet case, you can also calculate the set of priors in a fairly simple way, but let me just skip this in the interest of time. But it turns out that you can do it very nicely. And so let me give you just a couple of examples which also link to the next talk. So for instance, in the case of multiplier preferences, you can actually calculate the set C using this. So using the differential techniques provides you with a tool for calculating C. And so you can actually show that in the multiplier case, implicitly, the decision maker thinks that the ambiguity is total. Okay? So a decision maker who chooses according to the multiplier preferences is behaving as if there is complete ambiguity. Okay? A little bit extreme. KMM preferences. Here we have, so let me remind you, these are the standard KMM preferences. In the case of S of a state space which is finite, and in the case in which this distortion function is continuously differentiable, which is 90%, 99% of the things we think about are continuously differentiable anyway, then you can actually calculate precisely the extreme points of a set C, and they look like this. Now, I'm not claiming that this does look very nice. Let me give you some examples. Suppose that the phi function is given by the Cara function, okay, exponential, And suppose I make no assumptions on mu. This is the difference between this and the multiplier model. In the multiplier model, the mu function is the Dirac on a specific prior. Then you can show that the set C is given by what? Well, unsurprisingly, it's the support of mu. So in this special case, the smooth ambiguity model gives you an intuitive idea of what ambiguity is. And you say, well, it's the support of the second order probability. And yes, that is correct. However, this is not in general true. If your second order utility is a power second order utility, then in this example, we find a situation where the set C is actually a strict subset of the set of the support of mu, because the support of mu here would correspond to the case in which alpha is any number between 0 and 1. Okay, now this is constrained, it's smaller. So this is an example where the ambiguity that is revealed by preferences is not what you would think it would be naturally in the model, but it's a smaller set. Similarly, let me just wrap this up. So, this is the general case where S is not finite. And in the other models that I showed you before, variationals, concave, and so on, you can also use these differential techniques for calculating precisely what is the aspect of C. And so, let me just wrap it up. All of this to show that there is a way of describing the ambiguity in a problem, and as it happens, because of these differential techniques, for some number of practical models, we know how to calculate that. Again, going back to the policy question, okay, so for the policy question, the issue then is we can use these techniques to basically say, are the policymakers, for instance, behave, I want to make sure that the policymakers are really trusting the information that the scientists are giving them, are behaving according to the information, okay? They are imposing further constraints, political constraints, but I want to make sure that these further constraints do not change scientific evidence. This is a way of verifying this. Okay, so if like the best practical spin I can give to the exercise I've performed is this. Okay, a way of verifying that your assumptions, that the assumptions of the scientist are respected by the decision maker. Needless to say, there is an open issue as to whether we really want to do policy making using max-mean rules, and so being extremely ambiguity averse, or whether it might be more sensible in some situations to have rules which are a bit more flexible, and in that case, of course, everything else that I told you becomes useful.
So I'm going to talk. So as I mentioned right at the beginning, I work on decision making under ambiguity. I'm an economist and economic theorist, and I work on formulating models which take into account ambiguity, decision making under ambiguity, frameworks for those, theoretical frameworks, and also applying them in economics of how people decide in financial markets and so on. So I do a bit of both. And I'm very grateful to Michael and Christian and the organizers for inviting me here. It seems great. For a while, I've been trying to think about issues of how the frameworks that I've been working on and so on, whether they could be usefully applied in kind of problems that you guys here think about and policymakers use from what you have to say. And this seems a very efficient way to at least get a start on it. From what I have to tell you is my first thoughts about it. So about frameworks, the framework of ambiguity, how it might be used here, and so on. And these are first thoughts. I hope there'll be much better thoughts by the end of the afternoon tomorrow. And I will basically, I will talk about a particular framework, the smooth ambiguity model, which Paolo has given an introduction to. I will base my talk on this framework, which I have been along with co-authors Massimo Marinacci and Peter Klebanov, developed some time ago. I will talk about this framework in a couple of versions, sort of an intuition of the very basic version, and then a dynamic version. I will try and give you the intuition of what exactly what concerns of the decision maker. So that when I say decision maker, think of the policy maker, not the scientist. Okay, what concerns of the policy maker can it capture, or is it intended to capture? Okay, I will try and show with the model how it can be relevant and why it may be relevant to policy decisions of climate change. And as I said, these will be the first thoughts. And also, finally, I'll try and get to, it's more to do with how the model can be relevant, is sort of deeper into it, of calibrating the model to the calibrating ambiguity, ambiguity aversion, to parts of the parameters of the model in particular policy decisions, how the model may be applied. So two parts, basically: intuition, the basic intuition of what the model tries to capture, and I suppose ambiguity frameworks, and how it can be applied, and that the intuition, the basic intuition about the application of intuition is something that comes from application in economics. So that's I haven't done any work on climate, but that's what I'll try and explain. So these are so the talk is based on three papers essentially. Two are the basic the decision frameworks, which I worked with, as I said, with Peter Klebanov and Massimo Marinacci, and the third is work in progress, which is an application to financial markets, to asset pricing, with Fabrice Collard, Kevin Shepard, and Jean-Marc Talon, and I'll explain a bit of what we get from what. Okay, so uncertainty in policymaking. We've heard a bit about, quite a bit about it in the first session, and let me try and relate a bit to that. So, informed policymaking. Think of such a situation, so where which might not be common, but why shouldn't we be ambitious? But and so we start with a model structure, okay, and values of model parameters, as they say there, inputs, to obtain probability distributions on outcomes of interest, okay. So let me go further. So in what we are interested, this conference is interested, so a model could be some, these are things I learned very recently. So a general circulation model, we've been talking about, and there could be more than one, of course, as was pointed out, more than one, various degrees of complication, or even the least degree of complication, a simpler model. Okay, these are all different models, and they can give, they have different implications about outcomes. Okay, in terms of what they predict, their predictions. Okay, these can be different models. Even within a given model, a given GCM model, for instance, you could have parameters, okay? So parameters which determine the outcomes. So parameters of the model could be greenhouse gas and sulfur aerosol concentrations, emission rates or current concentration. These are parameters that determine. Similarly, the heat uptake, the oceanic heat uptake, this is a parameter, okay, which you have to measure. Or we had this debate on climate sensitivity. So, all these different. And by outcomes, I mean things like, say, precipitation, temperature, sea level rise, and various things. Why are they outcomes? Because we can condition the implications about economic output, okay, on these things. We are interested in these because they give rise to various, so GDP, the consumption, etc. Okay. However, I don't have to tell you, there's uncertainty about the model. What is the right model? Okay, in this room, we've just heard talks about various models, various distributions. So which is the right model? The policymaker doesn't know, and doesn't know for a good reason because the scientists don't know. Okay. Similarly, there's uncertainty about the valuation of the parameter. What is the right value? What is the right value? We don't know. We have some signals. We have past data. Okay. Even if we were to know what the value is today, we do not know how it evolves. What it will be 50 years later. Okay, things like that. And so given, and the point is with the uncertainty, might be of a very devious kind. Okay, so one, there's the historical data about these might be just a very small run of historical data, okay, about these parameters, or even being confidence in the models. Okay, we can't pin down. Okay, there's a lot of uncertainty about the parameters. There could be even, as was mentioned, different experts can have different views of what is the right model. At the end of the day, as I said, why is this expert necessarily right? You might have some confidence about one expert rather than the other, but okay. So the standard Bayesian model would be about that you have some priors about either different models or different parameter estimates, and you average across the models. Okay. What we'll talk about today is some way generating what ambiguity aversion literature, one way of thinking about it is generating policies or identifying policies which are a little more, has a feature of robustness across these different models. Okay, policies that may not be optimal given a particular model, but they don't do worse very badly under different scenarios. So you want a policy which might be, which is, since you have uncertainty about the various models, that is robust across them in some sense. Okay, so it tries to formalize that and tries to get to that, provide a framework to identify that. That's what essentially it's about. So you might be interested in a policy which has a certain mix of adaptation as well as mitigation, okay, which defensive in some way, okay, for instance. Okay, so Paolo, so let me explain the intuition of how the smooth ambiguity preferences give a rise to this. We want to get this idea of a robust decision, okay? So what do you say? So Paolo introduced this formally. So let me try and identify a bit components of this model. So what you have, it's a kind of a double expectation, as Paolo was explaining. So it's inside the first, So inside what we have here, so is one expectation. This expectation is, this inner expectation is with respect to the different possible probability distributions. Okay, so this is one possible probability distribution over outcomes. Remember, outcomes were things like the vector of precipitation, etc. Okay, those were outcomes. Okay, which are identifying the state of the world. Okay, f of s is an outcome from a particular policy in a particular state of the world. Okay, so f is a particular policy. The pi of theta, this is a particular probability distribution over S, so you can think of forget the uncertainty across models. Suppose we have one GCM model, but different possible parameter configurations, values of parameter configurations. Okay, so pi of theta corresponds to the probability distribution obtained, the likelihood obtained, okay, from one particular parameter configuration that is possible. And this is the expectation. You can forget, utility function here is about risk. You can forget that for the moment. It doesn't matter to fix intuition. Just think of this is the expectation from one particular probability distribution generated by one particular parameter configuration. Okay? This mu is a second order probability. You can think of it. Okay? A kind of a Bayesian prior or posterior over these parameters. Okay? Phi, in case, is a map, which from expected utilities means the numbers here to which essentially the phi function, the shape of it, gives the ambiguity attitude. So to understand that, suppose phi were affine, okay, just linear. We are back to Bayesian model averaging. Okay? So it's just standard Bayesian model averaging. If phi, on the other hand, were concave, what it gives is the following. So think of, so here we can think of expectations, okay, on this on the horizontal axis. So expectations corresponding to theta, theta prime, theta, all different possible expectations, okay, of the policy outcome, okay, or expected utility more generally, the policy outcome. Given the second order prior, the mu, we have a possible probability for each of these. So a probability distribution over the possible policy outcomes. Okay? What having that concave function does is when I think of one policy f, which has a probability distribution, gives rise to such a probability distribution, and another policy which gives rise to a squeezed policy distribution, say G. If phi is concave, the decision maker prefers this, okay, which has a less spread, a smaller spread of outcomes. Okay? That's basically, so it's a more robust. So it doesn't, the decision maker, the policy maker doesn't like the spread of outcomes over there. Okay? So it prefers. So very, very briefly, then it's basically the way it departs from the Bayesian model averaging is for each policy, it thinks, oh well, it has this prior, the mu, but actually the decision maker doesn't trust that prior very much. Okay, if phi was absolutely linear, decision maker trusts it as any other lottery distribution, but when phi is concave and more concave, it's a less trust. These experts, I might. So there was a suggestion. If I don't know very much about the experts, I just take a uniform prior. But then this is I'm using principle of insufficient reason. That's not a very good. We all know. I don't want to rehearse. That's not a very good principle to go by. I'm taking, since I don't know very much, it's a uniform, but it's a weak prior. Okay, so I want to be robust for that, and this would do that. So this is what it gets you. This is, and you can, and max min, as Paolo explained, can be shown as if I take the worst case scenario. So this is as concave as you can possibly think. That's taking the mean of all this. Okay, so this is doing that. Okay, let me try and go. So I kind of explained this. So here this is just a summary of what I was just saying. Let me go quickly on to the next framework, which is this is the basic intuition of the smooth ambiguity framework. However, most policy-making cases are not once-for-all decisions, as it says. There will be opportunities to learn along the way. Okay, in reality, climate policy will be revised, as we continue to learn, about various things, and therefore policy decisions are better modeled as sequential decisions under uncertainty. So we need a framework that does that. Okay. Now I won't go into again a lot of details, but basically this is a dynamic version of that, and I'll just explain just two things about it. So it kind of is. It's basically it has two properties. okay, which I just wanted to, just the last bullet point, okay. Okay, so two things. One that's missing, I should have been careful with my slides. So there's a mu out there, which is that the mu, remember the second order prior, that's just updated along. So you have an event decision tree, and you just update it as the world unfolds. Okay, update the second order prior. You get more or less confidence on a particular parameter configuration or a model, etc. And as you go along. Okay, that's where the dynamics comes from. These preferences are dynamically consistent. It's a decision theoretic terms economists use. Essentially, all that the bottom line there is the decision makers are forward-looking. They look forward to if such and such event happens, this is what I would do. They take that into account and when they make their decisions now. Okay, in that sense, forward-looking. Consequentialism is another decision theoretic concept. To the extent, basically, it says let bygones be bygones. Okay, so at any node of an event decision tree, all I care about, or the policymaker cares about, is the payoffs that's going to come after. How we got there, they don't. Okay, these are the two key elements that go into this. Let me explain next, as I said I would, very briefly, since I know I have just 5 minutes, very briefly about how the ambiguity can be modeled. Okay, so the second order prior, an example from that. I'll do an example of from where we applied it to basically a model of economic growth. So this was in finance and asset pricing, but it's the following. It's like as if the growth of the economy follows these two equations. Okay, so where this is the log of growth rate. There is a mean growth rate, and then it is also affected by a hidden state, what the true state of the economy is. Okay? This can't be observed. You can think of it as the growth rate that you observe is a signal of the true state of the economy. Okay? And the real economy evolves. Okay? So what it was yesterday has this is a persistence factor, has something to do with today. Okay? And you can see the growth rate itself, this is the mean, plus the mean changes because of this persistence from what it was yesterday. Okay? Engineers will see it, and scientists will see it, and you know what I'm talking of, basically the Kalman filter model I'm trying to. Okay? And essentially, as you know, and you can think of here, just as I've done growth rate here, you can think of your more, the various parameters I was talking about for climate change. Those are again signals of what the true state is. You don't know, so that's sense all this applies. But let me explain. So here, the first order probabilities, the pi theta, are given a particular xt. That's a parameter. Okay, what today's mean is, okay, of the growth next period. And that mean evolves, okay? So that's the pi theta. The second order, the mu t, is again a normal distribution over what this mean is. Okay, just think of if the scientist is just think of again in the Kalman filter, okay? So you're tracking the hidden state and that. So hidden state can go up and down depending on how you get the signals, okay? And what we do as a variant to this model, so you see a bad growth, then you think of, if you are possibly in a bad state, you revise your growth. That's where your forecast of the growth rate, okay? What we actually do in the model in our paper is a variant of this, and which I think would be useful to understand something. So we actually allow for the fact that it turns out that the rows, this persistence factor, is very hard to measure. Okay, and it turns out it is something like a row of 0.2 and a row of 0.85 are just about equally likely if you look at the data, this persistence. Okay. In other words, it's a kind of uncertainty like, we all know we are in a bad state of the economy today. What we don't have a very good idea about and a big uncertainty about is how long will it last? How deep is it? It's not that it is not bad, okay? And this kind of uncertainty allows for whereas if I behaved as if I knew rho, the uncertainty doesn't change. The x hat, the filtered state, goes up and down according to the growth rate. But the uncertainty given by these bands of confidence, that really doesn't change, the second order. However, if I have this uncertainty about these two rows, with the persistence, okay, and you can translate the persistence even in climate change things, okay, you can easily do, I'm pretty sure. You actually get the uncertainty varies, the ambiguity varies, okay, it goes up and down. Why does it vary? Just to give an intuition, basically, when the forecasts from the two models differ substantially. So the ambiguity, so learning can actually increase ambiguity time to time. When there has been a run of recent signals which make the two I did not wish to add to the ambiguity, which makes the forecast of the two models differ widely. Okay, so we heard examples of that. So things like tipping points and so on. Okay, these would do exactly that. That you have a run of signals where, based on which, condition on which you get very different forecasts. Then the ambiguity, and that comes out exactly here. So this is actually on GDP data. As you can see, things were very nice. 1990, after the 80s thing, the uncertainty, look here, it increases because of the sudden change in the growth. So I want to stop there. There is stuff more about calibrating ambiguity aversion and so on. Okay, thank you very much. That's very, okay, kind. Okay, so this is the ambiguity. So let me say a few things, not very much, I won't, about the ambiguity aversion, or at least what we kind of do, what I'm more comfortable in doing in descriptive analysis that I do in economics. So Paolo talked to you about the Ellsberg. I'll just briefly explain, not even explain, and just say the idea, what it is, state the idea. Here, you can experimentally, looking at an experiment, behavior in Ellsberg kind of situations, get an idea of what the parameter, ambiguity aversion parameter is. Okay. Now I'm more comfortable in saying, well, that's okay. That's useful to me when I'm doing descriptive economics and when I'm trying to say something about how ambiguity affects asset prices and so on. I'm less comfortable, simply because I haven't thought it through completely, about why that is so useful when I'm thinking of a policymaker. Why should necessarily, because after all, as I said, this another way to think of this ambiguity aversion parameter is the concern for robustness. Why should necessarily the policymaker be as concerned for robustness as the average undergraduate student that you put in an experiment, or someone playing the financial markets? Could be different. I'm not sure, but at the same, you could argue, for instance, well, the policymaker is, after all, representative of the society and should think. So anyway, so these are various things. We could also look at the next slide is about how one can also infer from market behavior a level of ambiguity aversion, which again can be useful. But we already know from the Stern report and so on, there can be debate about whether the market is the right way to think about it or not. The similar issues arise, and I'm not. I think I'll stop there. Thank you. Yeah.
So I will be talking about belief formation and ambiguity and learning from data. And the starting point of this project, which is joined with Jürgen Eichberger from Heidelberg, is that the standard decision theory allows us to model information in two ways. Either we have objective probabilities, in other words, we have a lottery and we know for sure what the probabilities of the different outcomes are going to be, or we have subjective probabilities, which essentially means that we are allowed to form any probabilities that we like. Now, real-life situations are rarely like this. It is rarely the case that we do know the probabilities, especially in the type of questions that we are interested in this conference. It is also usually not the case that we know nothing at all. It is usually that information arrives in the form of data points, and the case-based decision theory that has been proposed by Gilboa and Schmeidler allows us to capture this idea of learning from data. However, the drawback of the case-based decision theory is that it does not allow us to separate meaningfully utility and beliefs. And this is, of course, useful, especially when we want to make policy choices, because there's something subjective about utility, which we, which we would not want to impose on the society as a whole. Well, there might be something more objective or rationalizable about beliefs, and you might want to be able to persuade someone else that the beliefs that you're entertaining are, in some sense, correct or rational. So here we'll look at how beliefs form if information arrives in the form of data. And the first model to capture that is the one by Biot, Gilboa, Sammet, and Schmeidler in their 2005 paper. They provide a model which captures frequentist beliefs. So in other words, whenever you look at a data set, the probability distribution that you form corresponds to the frequencies that you observe in the data. However, of course, this neglects two important issues. It neglects learning from data, and it also neglects the fact that data might be more or less ambiguous. So here we want to capture the ambiguity that is contained in the data by looking at two types of such ambiguity. First of all, the data might contain different numbers of observations. And if we are talking about a statistical experiment, then as data accumulates, we will be able to learn more and more about the probability distribution. We will be more and more certain that the probability distribution corresponds to the frequencies which we observe. So this type of ambiguity is going to disappear as data accumulate. However, there's also a second type of ambiguity, which is particularly relevant for environmental issues, and it has been mentioned in the very first session this morning. Oftentimes, we just don't have the adequate data that allows us to make good predictions. And it is not the case that we can simply go on and experiment easily for the sake of learning alone. So in this case, if we have inadequate or missing data, there will be persistent ambiguity that does not vanish even as data accumulates over time. So the first part of the project is concerned as how do we associate beliefs with data. The second part of the project is actually more practically in the sense, it's a theoretical project, but the question might be considered practical. How do we make decisions based on data? And as I said, we're looking to separate utilities and beliefs in some meaningful way, and we would also want to incorporate ambiguity and attitude towards ambiguity into the decision-making process. So here's the model. This is just a notation. I'm going to try to put it into an example. So think about an expert who is going to recommend a specific policy or a specific course of action for a region that is trying to implement an environmentally friendly program. So you can think of X as the characteristics that describe the region, whether it's the specific geography, or whether it's urban or countryside area, and so on. A is the specific action that is going to be taken. So think about the region that is thinking of reducing CO2 emissions. So it might be that they're looking into investing into solar energy or using wind energy, or maybe incentivizing people to conserve energy more, and so on. R is the outcome of this project. And for a region which is going to be characterized by x0 and is planning to take a specific action A0, think now about an expert who will who will have to evaluate this project for this specific region. So the question is, we want the expert to make a prediction about the probabilities of the outcomes R for this specific scenario. The expert is going to have a set of observations, which we call cases. And cases consist of these triples, a characteristic or a different region which has undertaken some similar project. A is the project that has been undertaken. R is the outcome that has been observed. And it might, of course, be that the same region has been running the same program for a long time already. So you have a data set that consists of what you might call a statistical experiment with respect to x0, a0. But it might also be that this data is not available, so you want to use data from similar regions which adopted similar projects, and so on. So the data set is going to consist of such observations. T is the length of the data set, so might be more or less exhaustive. And the decision maker is going to come up with a prediction which characterizes his beliefs about the probability of outcomes. Now, we assume that this prediction does not need to be a point prediction. And I think this is important exactly because sometimes in policy choices, you would want the expert to express not just the mean of his beliefs, but you would want him also to express the uncertainty that he faces. And this can be done by giving a set of probability distributions rather than a specific point. And then the policymaker can take this ambiguity into account when making choices. So what we do here is we take the decision situation as something given, and we impose axioms on the predictions of the expert, which are going to lead to the following representation. So let me spell it out slowly. F is the frequency of cases that are observed in the data. P hat is a probabilistic prediction. S is the relevance of cases to the problem that the region is facing, x0, a0. So think first about a situation in which exactly the same case has been observed T times in a row. So exactly the same region has taken exactly the same project for many, many years. This is the data set that you have. And the same outcome has been realized. Now, in this case, you would assume that the expert will feel relatively certain about predicting that the same outcome is going to repeat itself. So in this case, the prediction, capital P hat T, is going to be the singleton, which places a probability 1 on the outcome that is actually realized. So in this case, the frequency of this case is 1, and the relevance, because you're looking at a statistical experiment, the relevance of each single case is the same, and you can think of it as being 1. So if you have a long data set, then it makes sense to make this point prediction. If you have a shorter data set, however, if you have, say, just 10 or 15 observations, then the expert might not be certain that the same outcome is going to realize again. So in this case, rather than having a point prediction concentrated on the outcome that has been observed, you might have a set around this point, which is captured by the capital P hat, which signifies the amount that this is the set of probability distributions that the expert is going to come up. And it captures the degree of ambiguity that he sees to be present in the data. And as I said, as the amount of data accumulates, this type of ambiguity is going to disappear because it comes from controlled statistical experiments. Now, if you have observed different outcomes, but for the same region and the same project, what you're going to do is you're going to simply weigh them by the frequencies, by F. And the same logic applies. However, oftentimes, as I said, your data is not going to be an exact statistical experiment, so you need to take into account different cases which are not exactly identical. In this case, S, the similarity function, is going to tell you how relevant each of these cases is for the decision to be made. And in this case, it is also going to be true that ambiguity is not going to disappear over time. And there are many examples of this in statistics where people deal with issues like missing data, and they show that ambiguity or the probability distribution cannot be point identified. So similarly here, if the experiment or the observations that you're doing are not exactly suited to x0, a0, in the limit you'll observe a set of probability distributions. So in this way, we capture the two types of ambiguity, that for randomized statistical experiments, the set of predictions is going to converge to a point, whereas in the case in which the observations are distinct, ambiguity is going to persist in the limit. The model allows you to incorporate a variety of very common statistical models. So frequentism is an obvious special case, but it also incorporates Bayesian updating. So you can have single priors and update them in a Bayesian way as you accumulate information. It also incorporates the special case of updating with multiple priors, in which you update each prior according to the Bayesian rule, the so-called full Bayesian updating. It incorporates kernel classification, in which you use similarity of observations to make predictions. It incorporates the case of missing data, and these are just special cases, so obviously the model allows for combinations of these. The model also allows you to choose a specific probability distribution out of the set that has been predicted. In particular, I'm not talking about the axioms right now, but you can see them in the paper. But if you believe that in the axioms that we impose when we're talking about set predictions, then, and if you use one of the standard rules that have been applied in the literature to choose a probability distribution out of a set, then this rule is going to also satisfy the axioms. So in particular, you might be acting as a Bayesian with a specific prior and pick a set. This is going to be consistent. You might be picking the center, in some generalized sense of the word, the Steiner point of the set of probability distributions. You will be satisfying the axioms of our model. You can be a max-min person and pick the worst probability distribution for each action. You'll be satisfying the axioms. You can also be an alpha max-min person in the sense of putting a weight of alpha on the worst and a weight of 1 minus alpha on the best probability distribution. All these possibilities are captured. And finally, a feature of the model is that the perceived relevance of cases is constant. It does not depend on the content, and it does not depend on the length of the data set. And this is both a plus and a minus of the model. It is a plus on the model because it imposes some structure, and it allows us to derive a representation. At the same time, however, you might think that as time evolves, you will not only be learning about probabilities, you will also be learning about structural properties of the model. You will be learning of how different cases actually correspond to each other. And this is something that we haven't been able to capture yet. I guess this is not because it is difficult to come up with axioms that would give you specific ways in which similarity would be changing, more because we're not sure what is an appropriate way to learn similarity from data. So I think this hasn't been discussed much in the literature, so this is the reason why our model keeps it this way. So up to now, I've talked just about belief formation. You give me data, our expert is going to tell you what are the beliefs in terms of probabilities, of sets of probability distributions. Now I want to talk a little bit about preferences over actions. And to do that, I'm going to use the Augsburg paradox, and I'm going to try and generalize it to incorporate incoming data. So suppose that actions are bets on the weather at a certain location. So think about a community that wants to use, to either use solar energy or wants to use rainwater for domestic purposes. So bets are on sun or rain. I'm going to assume that these are two mutually exclusive events. So now we are looking at two locations. In the one, we have observations over very long periods of time, and we know that the weather is sunny with probability 1/2 and rainy with probability 1/2. On the other location, we have no information whatsoever. We've just discovered a desert island somewhere, and we know nothing about it. Ambiguity-neutral behavior in this situation would predict that if you prefer to bet on sun in location number 1, you would rather bet on rain in location number 2. So because the two are mutually exclusive events, if you're assigning probabilities, then it means that sun being more probable at location 1 means that rain is more probable at location 2. Ambiguity-averse behavior, however, which is what is mostly observed in experiments, says that most people would prefer to bet on the outcome in location 1. Therefore, they would prefer to bet on sun in location 1 and on rain in location 1. So Ellsberg's paradox, of course, relates to a very special case in which you have all the possible information you could hope for in the one location and no information at all on the second location. More generally, you can think about the two locations as differing with respect to the amount of data you have about them. In particular, it might be that at location 1, you have a longer data set that is telling you that rain and sun occur with equal frequency. And at location 2, you have a shorter data set telling you the same thing about the frequencies. So now, of course, I haven't run the experiment, but I would claim that most people would prefer to bet on the location for which the longer data set is available, because a longer data set corresponds to a situation which is less ambiguous for them. So if you want to capture ambiguity-averse behavior, then preferring the bets on the location with more data points is probably sensible. So what we're trying to do in the model is to capture this type of preferences. So now preferences on actions are going to depend on the data that you have. And the preferences are modeled in the following way. VFR is the standard von Neumann-Morgenstern utility function of our outcomes. So it has all the properties that you know about. And the second term is a representation of the decision maker's beliefs. It has the same components as the beliefs that we talked about before. So in particular, it is taking into account the frequencies in the data. It is taking into account the relevance of observations of different actions, maybe not exactly identical, but different. This is the S of A and AC. And it is taking into account the probabilities that are assigned to A paying off a certain amount R after observing the same case, AR, T times in a row. So what you're not seeing, so in that sense, the representation separates utility and belief. The utility is independent of the action, and it is independent of the content and the length of the data set. Whereas the beliefs depend both on the action and on the observed data. Beliefs, however, differently from the standard expected and non-expected utility theory, are formed based on observations. And they reflect both the frequencies, the objective specification of the data, as well as some subjective aspects. How relevant do you think a specific case is to the action that you're evaluating? And what is your attitude towards the ambiguity that you perceive in the data? And the similarity function, the perceived relevance, is still independent of the content and the length of the data set. So again, we can use this representation to capture the two types of ambiguity. And in particular now, if you control for the frequency of observations, longer data sets can be considered to be less ambiguous. And as the length of the data set increases, the beliefs should converge to the observed frequencies of our outcomes as long as we're talking about controlled experiments. So here's a way in which you can try and measure the ambiguity attitude of a decision maker. So think about two data sets. One in which you are trying to predict the action A, and you have observed A giving you an outcome of R t times in a row, and another data set in which you have observed the same things, only k times t. So what would be the difference where would the difference in the evaluation of these two data sets come from? It can come from two aspects. On the one hand, so if I'm not going to assign to these two data sets an evaluation that corresponds to observing R with probability 1, then it might be that I'm an optimist. And I think that when I don't have sufficient information, the good thing is going to happen to me. So I'm overweighting the probability of good outcomes. Or it might be that I'm a pessimist and I'm overweighting the probability of bad outcomes as compared to the frequency. So when our model allows us to identify this degree of optimism and pessimism by approximating the evaluation of this data set by long data sets, which are presumably unambiguous, which contain only the observations of the outcome R, of the best outcome and the worst outcome. And when we do that, we can represent beliefs as a weighted average between the actual observation. Delta R is the probability distribution that gives a probability of 1 to the outcome R, the actually observed outcome. Some weight given to the best possible outcome, and some weight given to the worst possible outcome. And now you can interpret these three weights. Alpha is the degree of optimism, whatever you put on the best possible outcome. Beta is the degree of pessimism. And the sum of these two is the subjectively perceived degree of ambiguity. The nice features of the model are that the degrees of optimism, pessimism, and the degree of subjectively perceived ambiguity are independent of the outcomes. They converge to 0 as time goes to infinity. And the relative degrees of optimism and pessimism are constant over time. So it is only so alpha divided by gamma and beta divided by gamma are constant. So I think 5 to 10 minutes? OK. So I'm going to talk a little bit about why this might be interesting as this is the last part of our project, which is not very developed yet. So these are more ideas than results. So suppose now that you have modeled people who indeed can learn and respond to data by choosing actions. And suppose now that we have a society of such people, and they can decide, based on the data that they observe, which action to choose. So the idea here would be to model a society in which both optimists and pessimists are present. And maybe that can help motivate why it might not be the best possible case to only have pessimists, to only have max-min as the rule of choice for society. So suppose that new actions arrive sequentially. So as time evolves, you get new opportunities coming in. And for the purpose of the example, I'm going to assume that there's an objective probability distribution. Each action has a deterministic payoff, RA. And RA is IID across actions. So actions arrive sequentially. They have IID payoffs, and payoffs are deterministic. Once you choose the action, it's the same payoff that it pays. Of course, our decision makers are not going to know the payoffs of the actions, and they're not going to know the distribution. So they don't know that payoffs are deterministic, and they don't know what the distribution is. They can only choose one action at a time, and they observe the payoff of an action only if the action is actually chosen. So in other words, if you don't try out solar energy, you don't know whether it pays off or not. If you don't start a specific program, you have no idea of what the payoff is going to be. So the only way in which you can learn is by experimenting. And on top of everything else, people are short-sighted. So you cannot persuade them to experiment for the purpose of experimentation in order to learn more. You have to persuade them that this is indeed the best action to be taken now, given the information that they have. Now, what is going to happen in a society like that? So suppose you're Bayesian. And suppose even that you know all of the specification of the model. Then if you don't want to learn for the purpose of learning, you're going to be stuck at an action which gives you a little bit more than the mean, right? Because anything else is potentially going to be worse. It is worse than expectation. So you get stuck at an action which is a bit better than the mean. How much better depends on chance, right? Suppose now that you have a society that is only populated by max-min people. They're complete pessimists, and whatever ambiguity they face, they think that if they don't know anything about an action, they think that it is going to pay off the worst possible outcome. Well, this is also a pretty bad situation because such a society is going to get stuck on the very first action that they choose. They're never going to want to experiment at all. Think now about a society which is populated by extreme pessimists. Now, pessimists believe that if a new action arrives, then it's the best possible world, and they're always going to switch to the newest possible action. Again, not a very good scenario. Now, think about a society which is populated by both optimists and pessimists. And think about it in a way in which people can learn from each other's experience. So if someone in the society experiments with a new action, then the information that these people collect is available to everyone. Then what you would observe is that optimists are going to provide, so to say, the data for the society. They're going to be the ones experimenting with new actions, while pessimists would essentially assure that the actions that are actually good are getting adopted, that they're not left because of new actions arriving constantly. So a very, very, very preliminary result suggests that if new actions are not arriving very often, then you can make the pessimists in such a society choose the best possible available action at a time. So in this way, you would have a society which is in which the pessimistic people are learning gradually to choose better and better actions. So this is all I wanted to talk about. This is the conclusion that just summarizes everything that I said. Thank you.
Thank you. So the decision theory models look at fairly abstract sets of outcomes. And in this situation, you've got a really one-dimensional problem in the sense that it seems pretty clear that more CO2 emission will result in more severe consequences. A lot of uncertainty about how severe those will be at any level of emissions, and also some uncertainty about what the cost would be in reducing emissions to a given level, because it would involve technology that's in part present today, but in large part will have to be invented. But nonetheless, it's still essentially a one-dimensional problem. And what I'm wondering is does that help in any way in terms of dealing with ambiguity if you impose additional structure like that?
Yes.
Can I just say, so I mentioned for the past week I've been Googling a bit of some of the papers and my impression wasn't that it was at all such unidimensional. The different model predictions in terms of both of the various variables, the precipitation, temperature, etc. It's not just could be worse and worse. Pretty.
Well, what I meant is that the policy thing that we can affect is basically our CO2 emissions. So there may Well, the problem of what's going to happen is a very multidimensional problem. But the policy variable largely is how much CO2 are we going to emit now?
So I think I differ there too. I differ because so again, from what I read, so for instance, the policy mixtures can be quite complicated mixtures of restrictions on emissions. Both and even that could be quite complex in terms of the trajectory. But not just that, there's also mixture. So this is a mitigation, but there's also a mix of mitigation versus adaptation. So if it is true, for instance, that it is worse and worse, then we better also start allowing for growth and using growth to adapt. So it's quite a complex.
Just a very quick comment. Read Waxman-Markey and read the negotiating text for Copenhagen, and I suspect you will decide that the policy levers, even on the mitigation side, are not a single lever. There are thousands of levers. So it's a highly multidimensional problem, which gets us to limiting CO2.
Is to limit CO2 emissions, including setting up ways to capture it out of the atmosphere. Yeah. But in the end, the story we heard this morning was it's really CO2 levels that are driving this, and that the CO2 level in the atmosphere on a given date in the future, so maybe trajectory matters, but CO2 level in the atmosphere on a given date 50 years from now is a one-dimensional problem.
Sure, but if you were trying to write the legislation to get there, there would be huge numbers of uncertainties having to do with technology, economics, human behavior, what the guy down the hall is going to do, what your predecessor is going to do in the next Congress. I mean, so there's, if you're really going to do the problem, I mean, there's a huge degrees of dimensions of policy uncertainty on that part of it.
I think differently put, the problem, so it seems like the objective, which is, the level of CO2 emissions might actually be single dimensional. The problem is, from my perspective, the act space is far from being single dimensional. So that's the difficulty, right? I mean, it's it's a relation between acts, states, and outcomes that is far from being single dimensional.
Yeah.
Of course, if it were so let me rephrase my original question. If it were really a single dimensional problem, then it would be very simple.
Okay. But
can I? Sorry, one kind of follow up. Talking about the reduction of structure here, even if we have many dimensions of uncertainty and of outcomes, wouldn't be another way to think about it that most of the current ambiguity models try to generalize because there are very different preferences, and you might even want to have ambiguity-loving people in there. But if we actually think about it as a normative problem, like at least a representative of the state wants to do a decision, aren't there some of these axioms that we put in, or that we actually throw out currently, that we might want to put in again for normative reasons? Would there be anything that comes to your mind that would restrict our models to something more tractable due to the fact that we are not describing kind of arbitrary individual decisions, but kind of try to get in consensus of a society?
I think that was precisely what I started with, which is, I would say that probably 95% of the cases what you care about is max mean. Now, max mean has all the properties that we don't want to have. Ambiguity aversion in a strong form, certainty independence, and so on. It's not, it's open to debate, let's put it this way. It's open to debate whether that is really the type of decision you would like to have for society. It seems to me, it seems to me that there hasn't been really that much of a debate. It's like basically now everybody takes that to be the standard. But yes, I maintain my original position, which is it's not totally clear to do, to me what I'm doing here.
That's very interesting.
Oh, I think I think statisticians and econometricians also have a different criterion, which hasn't been discussed here because I guess none of us is working on it. But there's the max-min regret, criterion which is used by econometricians and which is being put forward as a decision criterion for policy making, but I don't think it fits. I mean, it's a different theory.
Then just because you said, and you wonder what you're doing here, is I totally don't believe that the max-min is like very attractive from a normative point of view, especially if you look at the axiomatic underpinnings. I don't think that any of the axioms are particularly convincing as opposed to the model you presented, as opposed to the model that Sujoy presented. So I really just wondered whether any of the axioms you used to get the more general axiom, because I also believe that we should have a different treatment, you think might be something, if you think about it from a normative perspective, you would be willing to throw it out. And I think you were actually, or I didn't see that you were actually convinced that the axioms you presented or skipped over it, but that you have in your paper, that you would say they are from a normative perspective, a priori, something that you would restrict, you make stronger to get like a simpler model. I found all of them actually to be normatively somewhat appealing, and wondered whether you can say that one of the relaxing these axioms wouldn't be normatively appealing. But
beware, you're sitting beside a psychologist. Yes, I mean, I would say my answer would be that I agree with you in terms of basically the axioms that are imposed in this general model are the weak order condition, which is, and I'm sure that, everybody may have issues with, especially the completeness part. Weak order is transitivity and completeness. Transitivity, kind of harder to disagree with, but you can if you want. Completeness is easier to disagree with. The other axiom, important axiom there is in the construction of everything that I showed you is the monotonicity condition. There is a kind of it's something that economists find totally natural, but again, once you start, looking at what people really do, then, as Amos Tversky used to say, give me an axiom and I'll design an experiment that shows that people violate it. So, but yes, normatively, I think these are kind of more defensible positions than the other ones, especially. Ambiguity, the strong ambiguity aversion axiom that I didn't really show to you, the ambiguity hedging axiom is something that I don't find particularly compelling, for instance. So and it's implied by max-min. Certainty independence, when it comes to normative considerations, I find it a bit harder to believe that you want to violate certainty independence. It's true that, again, we're talking about, if you're talking about a single individual making decisions about portfolio and retirement savings, then it may make sense to say, well, you want your ambiguity attitude to be wealth dependent. But if we're talking about society, maybe ambiguity attitudes could be wealth independent. So I find it a bit more defensible than the extreme ambiguity aversion axioms.
Could I raise one question? My question goes back to learning and the effect of learning on ambiguity. I understood from your presentation that in certain situations, learning could actually increase ambiguity rather than reducing it. And then now, as an economist, I take it from normative point of view, reducing ambiguity is welfare enhancing. So given that possibility, the question arises as to under what conditions, given the set of the axioms, learning is ambiguity enhancing or ambiguity reducing, and whether there should be some optimal degree of ambiguity.
So the ambiguity partly is exogenous to the extent that it is about how events unfold. What is endogenous and part of, just clarify something, and part of axioms is what I pointed out. So I had dynamic consistency. So that another way of saying that is that information is valuable. for these decision makers.
That's exactly the point, that if
Okay, so that is part of that model. Right. But at the same time, there could be events that increase ambiguity, I mean, very naturally, and we were talking about in climate a little while ago, and I was pointing out that that can happen in economics, just like right now. The uncertainty has increased. And one way of thinking of it is, think of economic experts you may have heard talking 3 years ago, how much they agreed and how much they differ now in terms of their forecast. So that's what was basically the intuition behind what I was presenting. The increase in ambiguity was there were these two models with slightly different persistent factors in the Kalman, which were giving in a way, they had two different, very varying forecasts. If the signals were such, the run-up of signals were such, would produce very different forecasts from these two possible models, then we say that the model uncertainty has increased. What is appropriate? The ambiguity has increased. So you can take actions which are robust to such things. That's one thing, but you can't control, I don't know what you mean by controlling the ambiguity per se. You take actions which are, you can take policies which as a monetary policy maker, which is more robust, but that's the sense in which I was talking.
Can I add something? Of course, there are ways of doing this. When you're dealing with sets of priors, you can, there are results that were famous in economics a few years ago. Now we kind of forgot about them. All these results about rational learning, so that you can actually show conditions that the priors have to satisfy, under which basically all the priors will eventually, as you learn, will eventually converge to basically towards a single prior. So there are conditions like that. Years and years ago, I was here in Berkeley as a graduate student, and I tried to think about something which I thought was very intuitive as a condition of diminishing ambiguity, which was to say, let's imagine that basically you would like the set of priors to shrink as time passes by. And then I immediately realized that this would not even be true for a Bayesian decision maker. Okay, like set containment is something that even a Bayesian decision maker would violate, right? Because if you have Bayesian learning, single prior Bayesian learning, the prior can shift around depending on what you learn. So these are tricky issues. Okay, so even very intuitive ideas, very intuitive geometric ideas don't work very easily. But this rational learning literature works. I mean, those results can be applied. So there are conditions that we can design. Of course, assuming that you have a priori decided how you do updating, which is one of the issues. Like in the KMM model, one of the nice things about the KMM model is that it provides a very simple and intuitive way of doing updating, whereas the more general models that I was talking about, in 90% of those models, it's not obvious how you would update sets of priors or how you update preferences dynamically, which is one of the reasons why the models with ambiguity are not as successful in economics as we would like them to be, because lots of people think that the dynamic application is crucial and it's not satisfactorily resolved.
Yeah, I don't think there are any really hardcore Bayesians here, but so I'll pose as one and ask, following up from Christian, a hardcore Bayesian would presumably say for social decisions we want to act optimally, and the optimal procedure is always Bayesian, that if we're not certain about our priors, that means we must have some higher order parameter uncertainty. We should probabilise that, keep going until we've got everything, then use reduction of compound lotteries to do the prior, then update that. So I guess I'm just interested in what responses you'd have to me if I were that Bayesian.
Well, Gilboa and Schmeidler have a recent paper that comments on the fact of why you might not want, why Bayesianism is neither necessary nor sufficient for rationality. And the main argument is that the prior is arbitrary in some sense. So, and there are many situations in which there's no good way to formulate prior and to persuade someone else that this is a good prior to be formulated. And they actually argue that in many social situations, the max-min would be a better principle on which to make decisions, because you can convince people that certain priors simply cannot be excluded. And the max-min ensures that you're going to minimize the damage in the worst possible scenario. But so this would be my response to it.
My response is the Savage quote. And by the way, you know, it's well known. If you read the Ellsberg paper, you will find out that Savage seemed to be falling into every possible trap that people set for him. And one he fell also in the, you know, for the Ellsberg paradox. And the Allais paradox, yes, of course. In the case of the Allais paradox, Savage said, oh, I think I made a mistake. Now that you told me, I would revise my preferences. In the case of the Ellsberg, that's what Daniel Ellsberg reports, he actually was troubled because he said, I'm not sure I would like to revise my preferences. Now, of course, you know, so I appeal to authority. That's my only...
Again, concerning the normative status of these criteria, there are some results showing the unpleasant consequences of deviating from expected utility, especially of violating the independence axiom. You're susceptible to Dutch books, and you might reject costless information. And I wonder which of these cases apply to these criteria under ambiguity, or similar arguments.
I can go ahead. Well, there are, yes, I mean, some of these can be seen as violations of what dynamic consistency. So there are actually variants of models that allow decision makers to care about ambiguity and yet not violate dynamic consistency. So some of these issues can be addressed. Some others no. My point of view is actually slightly Taliban on this. I actually think that it's precisely the violations of dynamic consistency that make the ambiguity models interesting. You know, that if you impose, but Martin Schneider was not here, Martin would have presented to us a dynamic model of, or at least may have presented that, a dynamic model of multiple priors in which you impose dynamic consistency, and this gives structure to the set of priors that has to evolve along, you know, in time in a certain way. It has a certain, this property called rectangularity. This is work with Larry Epstein. The problem is, if you apply to the Ellsberg paradox this assumption, you already get counterintuitive answers, because you kind of force the decision maker to be ex ante ambiguity averse and ex post ambiguity loving, which to me makes no sense. I agree. There are issues, but unfortunately, it's not clear that they can really be resolved without removing the appeal. As to Dutch books, I don't believe in Dutch books, so. I don't care. Never seen one. Yes.
Yeah, still on the question about axiomatic structure, which is the question was which is the best axiom that we might want to suggest to a real decision maker in order to let him her making the decision better than just max mean. Don't you think? Perhaps I already know the answer, but let me ask anyway. Don't you think that there is perhaps a too big gap between the papers that have each time a more complex axiomatic structure and generalized models encompassing other models into it and real decision making? You were saying that you didn't know what you were doing here because 90% or something like that of real decision making problems are max mean whenever. So one way might be let's not think about too much on what does it mean in terms of axioms of what the representation results. Let's just take some representations that are a bit better than just plain max mean and a bit more richer than max mean and able to encompass more practical behavior of real decision makers. And perhaps we might want to go backward and see what it means in terms of axiom, but let's not start in terms of what are the best axioms we have in mind to suggest to decision maker. Let's just start from what is the best or what are acceptable representation tools. In this, if this makes sense, then it's not too relevant if we take the multiple prior of the Choquet or the alpha male or whatever. What is relevant is if we take some of these representation tools that are a bit richer than max mean and able to encompass more real behavior. Let's take just an intermediate step between the heliosphere of the theory and the ground of the practical applications. What do you think about this?
I'm not sure I understood what you're saying. The one way to interpret what you're saying is absolute anathema to anybody doing decision theory, which is, who cares about the axiomatics? Let's just work with the decision rules. Now there is a bunch of people that do this in economics, but I don't want to associate myself with those things. I can go on with the usual spiel of why do we really need axioms, right? I mean, there are people that can do this much better than me, but the point is, the axioms provide you with a simple, and the psychologist knows this, simple and testable implications of behavior, which you can, use to refute the theory, and so on. As well as the axiomatic methods provides you with a way of making sure that you're talking about things that can be measured and can be observed, which is what the economists I just mentioned not necessarily do. So, no, I agree with you in terms of, applied work. Of course, who cares, right? I mean, I just find a model which is tractable and has some nice parameterization, and then I use it. In fact, to a large extent, the reason for the success of a KMM model is precisely because it has some very simple, very nice parameterizations. And you can use it, you can say, well, this is the phi function is Cara with this coefficient. The U function is CRRA with this coefficient, and then you can go on and work with it. And of course, I mean, even better than max mean, right? Because max mean has this disadvantage that what is the right set of priors? Of course, they have to still tell you what the support of a mu function is, which is so. I mean, it's clear that in applied work, you definitely have to. So if your point is, aren't you guys spending too much time doing esoteric, as I said, heliosphere type of work in terms of models? Why don't we work on more special cases? Your point is totally warranted. I agree with you. We should be wasting our time doing the special cases.
Any other salsa to Rick?
Just because we're getting on for lunch, so I thought I'd just ask a question. I mean, I appreciate all the axiomatic foundations. I think it's actually extremely important. But I have a certain feeling, a little bit like maybe a social choice theory in the 70s, that is all very deeply interesting from a theory point of view. So I'm just trying to be the advocate of the devil just before lunch. Now imagine you're a policymaker, and you come along with your models, and then you have to specify how risk averse you are, and then you have to have some ambiguity aversion, these two functions, it is U and this phi function or whatever it is. And then imagine a political context, a political context. So imagine then you go to Mr. Bush or you go to Mr. Obama. And then, I was a politician for a while, but typically what people do is if the models don't like what they do, they commission another report. And they say, well, for example, if I'm a bit brown rather than green, I'm a very green politician in a way, but if I were, I'd probably get hold of this Danish fellow or whatever, and get him to commission another report and say and give a lot of weight to that. So in a sense, that's kind of so what I'm kind of looking for is a kind of because you say, why is it not being used a lot in practice? And you say maybe it's because it's not tractable. I think there may be also deeper political economy kind of questions to be asked with these kind of decision theoretic frameworks. So if you're in a context with a number of, say right-wing countries, a number of green countries, or within a country there may be conflict of interest, where people are picking the information that most confirms their own prejudices. Now, in such a context, because the whole context of your models, which I love, because I think they're very beautiful, particularly the dynamic generalization, is of course very much of a social planner context. So is there anything you know where people have tried to go a little bit beyond the axiomatic foundation? I mean, of course, we know in economics we have a whole political economy literature as well, where you try to take account that it's more incentive compatible with the people who have to take the decisions. Is there much work done in that area and with true model uncertainty?
Well, there is, I mean, in macro, there is, I mean, that's, it is very practical based, actually. Not based, I mean, has been applied. I mean, in the sense of, instead of saying ambiguity aversion, they do talk about robustness, and which is where the way I try to, I mean, even for the policymaker here, I mean, you have those priors which are, you know, you don't really trust very much. There's either very little data or just basically some expert opinion. And all we are offering here as theorists is a framework. You know, if you are interested in a robust, what is a method of picking out robust decisions, that's about it. You know, how robust you want it to be, that should come from some political feedback. But given a political stance about, you know, I want some robust decisions, this is just a framework to pick out. You know, that's what axioms do. You know, we can't say which is normatively more. You know, you can, you know, axioms are telling you a little bit about what underlies this picking a more robust thing, and you know, with the hope that if you understand better, you will take a better decision. But all I'm saying is that once you have a stance, a political stance about a robust decision,
the Sergeant Hansen, all this macro stuff on robust,
on
robust
which
control.
Is a special case of this.
They all assume, of course, it's a special case. Yeah. It's related, closely related, but all that macro literature assumes a homogeneous decision maker.
No, not necessarily.
We get into some of these questions with the afternoon's papers.
Yes. Let me just say one thing. There is work. There is at least one person in this room that has been working on an application of ambiguity models to mechanism design, and it's not me. It's over there. So there is work that is being done now, trying to incorporate ambiguity issues into mechanism design, and so try to look at these things like robustness, but from the viewpoint of mechanism design rather than robustness from in that sense. So yes, there is a little bit of work, and it's an area which is actually subject of interest right now. So